Okay, so this chapter we're going to look at magnetic fields in matter, and we're going to start this lecture by looking at diamagnetism and paramagnetism. So if you remember when we were studying dielectrics, we found that the response of a dielectric when placed in an electric field is the formation and alignment of dipole moments. So here we have a dielectric material in between the plates of a parallel plate capacitor. So we have an external electric field from those plates. And what that electric field does is it's going to align or first create dipole moments if there aren't any naturally permanent dipole moments in the dielectric. And then once you have the dipole moments, it'll align the dipole moments. So that's the response of a dielectric when placed in an electric field. Now we're looking at magnetic materials. So we're going to look at the response of a magnetic material when placed in a magnetic field. And we're going to find it's the alignment of the magnetic dipole moments in the material. If the dipole moments align in the same direction as the magnetic field, the material is called ferromagnetic or paramagnetic. And if the dipole moments align in the opposite direction as the magnetic field, the material is called diamagnetic. So here, let's say here's our magnetic material, and here are the magnetic dipole moments in the material. At B equals 0, these moments are not aligned. There's enough thermal energy that makes it so that the moments are randomly aligned. If we now place a magnetic field in the vicinity of a paramagnetic material, the dipole moments will align in the same direction as the magnetic field. In a diamagnetic material, we turn on a magnetic field, the dipole moments will align in the opposite direction of the magnetic field. So now we're going to look at the response of a single magnetic dipole to an external magnetic field. So if we have a current carrying loop in a magnetic field B, and we say the current carrying loop has a magnetic dipole moment M that we see here. If we put Z in, the B field B in the Z direction, then the angle theta here is the angle that the magnetic dipole moment makes with the B field or the Z axis. So we're going to find the magnetic force on this current carrying loop of wire that's in this magnetic field. So there's going to be forces on the two sides here. We'll start with side A, the two sides A of length A. So let's start with this one here, using the equation for the magnetic force on a current carrying wire, integral I dl cross B. If we use the right-hand rule, dl cross B, we'll get the direction of the force in the x direction, so I hat, and then I do the cross product of dl, which in this case is just A, this length A, with B. The magnitude would be AB sine alpha. Alpha is the angle between DL and B. If I do the same thing over here to this side, the opposite side of length A, I get the same thing but in the opposite direction. So these two forces cancel out, the force on this side and the force on this side. Now I'm going to get the forces on the sides of length B using the equation for a magnetic force on a current carrying wire. So if I start with this side, B, using the right-hand rule, I get the direction of this force is in the y direction, j hat direction. And doing the cross product here, dl is b in this case, the length of the wire, b, and then the angle between my b field and this length of wire here, it's 90 degrees. So I get I little b b j hat. Doing the same thing for the opposite side, I get the opposite direction, same magnitude. So these two forces also cancel out. But we're going to find that these forces produce a non-zero torque on the current carrying wire. So we're going to find the torque produced by the two forces. So the torque here is going to be lever arm, which is A over 2 cross force, FB1. For this one, the lever arm is also A over 2 cross FB2. So I get, if I do the right-hand rule, both of these torques are going to be in the x direction. I'll do the right-hand rule visually in class if you don't see that. And then the magnitude A over 2 force, magnetic force on B sine theta. I can add those two up. They're both in the I hat direction. So I get A, the length, I current, B, the other length, B magnetic field, sine theta. Theta is this angle here between the magnetic field and the magnetic dipole moment. So the torque, I can write AB, that's the length times the width of the wire, that's just A, the area of the current carrying loop. So I can write the torque is equal to AIB sine theta I hat. AI is just m, the dipole moment of the loop. So I can write it in terms of that, little m. So I get the torque on the magnetic dipole moment m in a magnetic field B is equal to m cross B. So this is similar to what we found for an electric dipole moment in an electric field. The torque was equal to P, the electric dipole moment, cross E. Here we have M cross B. So we see that the magnetic dipole moment wants to line up with the B field. So we have these magnetic dipole moments in magnetic materials, and we see that if we place them in a magnetic field, they want to line up. So where do these magnetic dipole moments originate from in magnetic materials? Well, there's two places, two sources. There's the spin of the electron. You can think of electrons as spinning about an axis, and that creates a dipole moment. And then we have electrons orbiting around the nucleus that also creates a magnetic dipole moment. So diamagnetism results from the magnetic dipole moments. So the magnetic dipole moments that have a diamagnetic response to an external magnetic field originate from electrons orbiting around the nucleus. Okay, so those dipole moments there that originate from electrons orbiting around the nucleus, they will give rise to a diamagnetic response if placed in a magnetic field. So again, diamagnetic response meaning they will line up opposite to the magnetic field. So we're going to look a little closer at the diamagnetic response. So we're going to model the orbiting electron like a current loop. Okay, so here's the nucleus of our atom. Here's an electron with some velocity v orbiting around the nucleus. And we're going to treat that as a current loop. Current, we know, is charge per unit time. Here, our charge is an electron, so negative E. The velocity of the electron, it's displacement delta L over delta T. So the time it takes to go once around the loop, delta T, is going to be 2 pi rho. Rho is the radius of orbit divided by v, its speed. So the current created by the orbiting electron will be minus ev over 2 pi rho. Okay, so it's the charge over time. Here's the time, 2 pi rho over v, and charge, negative e. So the magnetic dipole moment of an orbiting electron is just its current times the area of orbit. So that's going to be, if I plug in the area, if it's going at a radius of rho, so the area is pi rho squared, and we get the pi's to cancel out. And this should be a rho, not an r. So one of the rho's cancel out. Let me change that. Okay. So we see that a change in speed v of the electron will result in a change of magnetic dipole moment m. Okay, here's the speed of our electron, and it's related to m, the magnetic dipole moment. So if we can compare the speeds before and after an applied magnetic field, we can show how an applied magnetic field changes the orbital magnetic dipole moment, m. So before a magnetic field is applied, the only force acting on the electron is going to be the electric force that it feels from the nucleus, the attractive force from the positive charge of the nucleus. And that force is just going to be the charge. If we're looking at like a hydrogen atom, so nucleus has charge plus E. So E squared over 4 pi epsilon naught, the distance between them, rho squared. And the direction of the force is towards the nucleus. It's a centripetal force. The electric force is the centripetal force keeping the electron in the circular path. Okay, so we say that electric force is equal to the centripetal force. Centripetal force we know is equal to mv squared over rho, the radius of the orbit. So now we're going to place the magnetic dipole in an external magnetic field. And in this case, I'm going to put the magnetic field in the negative z direction. And we know a moving electron in a magnetic field is going to feel a force, negative EV cross B. If the magnetic field is applied perpendicular to the plane of orbit, then the magnitude is just EVB, because we have a sign of 90 there. And the direction, if we use the right-hand rule in this particular case, if we look at the velocity, the direction of the B field, and the fact that it's a negative charged particle, we find that it is also towards the nucleus, that magnetic force. So now the centripetal force is the electric force, okay, the attractive force the electron feels from the nucleus, and this magnetic force, also going towards the center. So we add those two up to get the centripetal force. Rearrange a little. And so we're going to compare with the centripetal force before the presence of the magnetic field, which was just due to the electric force, the attractive force. So we compare these two, and what we find so we can set those equal. They're both equal to 1 over 4 pi epsilon naught e squared over rho squared. So I set those equal. V is the speed of the electron before we placed it in a magnetic field. VB is the speed of the electron after we placed it in a magnetic field. That's what I just say here, where V is the speed of the electron before the application of the magnetic field, and VB is the speed of the electron after the application of the magnetic field. So we can find the change in speed, VB minus V, from our equation that we found. So we want VB minus V. I rearrange the equations a little. I have a difference of squares. And I'm going to assume this delta V is small. VB minus V is small. If I can do that, I get my delta V is equal to E rho B over 2M. So when the magnetic field is turned on, in this scenario at least, we find that the electron is going to increase in speed. Its speed is going to increase, or the electron speeds up. So what does that do to the orbital magnetic dipole moment? M that we found to be minus EV rho over 2. So if you turn on the magnetic field, the electron speeds up, and therefore there's going to be a change in the orbital dipole moment as well. So the change in speed will lead to a change in M, the magnetic dipole moment. If I plug in what rho V is, it depends on B, the magnetic field. So I see that the change in M is going to be opposite the direction of the magnetic field. So this is a diamagnetic response. We turn on the magnetic field and the dipole moments change in a direction opposite that of the magnetic field. Paramagnetism, where we have a magnetic field applied and the dipole moments will line up with the magnetic field. The magnetic dipole moments that have paramagnetic response to an external magnetic field originate from the spinning electron. So the dipole moments created by the spinning electrons feel a torque, just like we calculated earlier in the slides in a magnetic field, and M cross B equal to M cross B. And this is a large effect in spinning electrons. It's a small effect in the orbital magnetic dipole moment. That's why we did not look at it for the diamagnetic response. But for the spinning electrons, this will be a large effect. And so we have a paramagnetic response. So we will look at these two clicker questions together in class. And that is the end of this lecture.